Take a look at this function. Hopefully you've seen this one before, right? It's f of x equals 1 over x. What I want to do is I want to talk about what the function is doing around 0. Again, obviously the function is undefined there, right? You can't define by 0. You can't divide by 0, and this limit doesn't exist, right? And we can see this, right? Good opportunity to apply our definition. If you pick any number, say, okay, let's see if that's the limit, right? Well, you pick any epsilon neighborhood around that point, and there is no delta neighborhood around 0 where every number in that neighborhood has a y value that's in this neighborhood, because every x value over here on the left-hand side goes down to a negative number, and that's outside the epsilon interval. Okay. We can, however, be a little more precise if we only look at this from one side, right? If we look at this just from the right-hand side, you notice I did change the limit a little bit, right? It says x approaches 0 from the right. Okay, now we can be a little more specific about what happens. If you pick a number close to 0, you get a big y value, and if you pick a number closer, you get an even bigger y value, right? You go closer, it gets even bigger, and the language we use here is this function is unbounded. And the way I'm going to write this over here with a limit, I'm going to say the limit as x approaches 0 from the right of 1 over x equals plus infinity. Or you can, I usually put the plus sign in. It's a bit of a habit. If you leave the plus sign off, just say infinity. That's fine too. Okay, now I want to be clear about this before we go any further. I am not saying that this limit exists. It does not. I'm also absolutely not saying that infinity is a number, like 3 or 7, the other limits that we've seen. Okay, all this is it's a notation. It's a way for me to say the function is unbounded in a positive direction when we get into a neighborhood of that point. And obviously, right, if you think back to the previous graph where we had the left-hand side, I would say the limit as x approaches 0 from the left of 1 over x is negative infinity. Okay, let's look at another function here. Take a look at this thing. You see, it's very similar, right? We're looking at f of x equals 1 over x squared, and I've got the graph over here. All right, so now in this case, you can see, we'll get to a formal definition in a minute, but you can see just by looking at the function, at the graph, that the limit as x approaches 0 from the right of 1 over x squared is plus infinity, and the limit as x approaches 0 from the left of 1 over x squared is also plus infinity. Well, we're going to follow the rule in this situation that was set by a theorem that we saw in the last lecture that said if the left-hand limit and the right-hand limit both equal the same thing, then that is what the, if you will, double-sided limit equals. So in this case, because the left and right-hand limits are the same, I would say the limit as x approaches 0 of 1 over x squared is plus infinity. And again, that's just a notational way for us to say the function is unbounded at 0, and kind of on both sides, it's unbounded in a positive way. It's increasing without bound. Right? And if you flash back for just a minute to your intermediate algebra, college algebra, maybe pre-calc class, right? These infinite limits that we're looking at here, these are the vertical asymptotes, right? In your pre-calc and college algebra classes, that's the language that's used to describe them, and you just kind of say, okay, look, this is what it looks like, so that's what we're going to call it. Now we have a definition. So this is our formal definition. And you can see it kind of it's still playing off of that whole epsilon delta concept, right? Only now we've replaced the epsilon, and we'll see why in a second here. We've replaced the epsilon with this f of x greater than b. All right, so what our definition says is that in order to say this, in order to say that the limit as x approaches c of f of x is infinity, for every b, every real number b, presumably fairly large, whenever we have an x value whose distance from c is less than delta, the function value has to be greater than that number. Okay, so let's look at our example here. This is still f of x equals 1 over x squared. What this is saying is that if you pick a b value, I have to be able to find an epsilon, excuse me, a delta down here, an interval around 0, such that every number in that interval, if you'll pardon my really bad drawing skills, every number in that interval gets mapped to a y value that's greater than b. Okay, so let's see how we can actually apply this. Right, let me clean up a little bit here. There we go. Just to show what I claim, to show that the limit as x approaches 0 of 1 over x squared is in fact infinity. Okay, well I'm going to say let delta equal 1 over the square root of b. All right, then what I have to show is that whenever this is true, this is true. Okay, so let's see. I'm saying the 0 less than the absolute value of x minus c is less than 1 over the square root of b. And well, c is 0. So this is 0 less than the absolute value of x less than 1 over the square root of b. And now let's square both sides. Right? This is saying 0 is less than the absolute value of x squared is less than 1 over b. Okay, well the absolute value of x squared is just x squared. Still less than 1 over b. And I don't care so much about the 0 part anymore. I'm going to let that go. I know that when I square something, it's greater than 0. Right? So that part kind of goes without saying at this point. Now what I'm going to do is I'm going to flip both sides over. Right? If I flip both sides over, I get 1 over x squared is greater than b. And that's what I needed to show, because 1 over x squared is f of x. Okay. So that's limits that are infinity. And again, please keep in mind this is just strictly a notation, right? I'm not making a claim that the limit exists. These limits don't. And I'm certainly not claiming that infinity is a real number. It's not. Okay, but this is a convenient notation, because sometimes we want a way to be able to say this function has this particular behavior, and this is the notation that we're going to use to do it. Okay, so what we've looked at here is situations where the y value goes to infinity. Right, what we're going to do in the next lecture, kind of the second half of this one, we're going to talk about what happens when the x values go to infinity.